Hey guys, happy Wednesday. I'm running a little late, had some issues with the cables. So, to be honest, y'all feel like you're real far apart. I know, it's probably a little nauseating. Someone moved around all of our equipment today, but I think that's about right. So, we have finished roughly, get this, 2/3 of the semester. We have 1/3 left. So we are starting the material that we'll see for the first time on exam 3. Hi, good job. So we're starting that stuff now. And then we'll just have one chapter after the exam. So next week is November, which I'm a little shocked about. So as you guys are showing up, sorry again that I was running a little late today. I forgot half the cables in my office and had to I came in the room where I teach and then I had to run back over there to get stuff. Whew, it's a hard life. So as we get started, anyone have any questions today? Any information about, so Jamie asks, will there be a study guide for the final? Nothing specific, but you can use any of the problem-solving worksheets. So what you have already is the worksheets for every chapter, the collaborative problem-solving, these worksheets that we do in here, or the exam reviews. I looked at the calendar, and there is not a exam review scheduled. As we get closer, I will see if there's interest in that, and we'll try to find a time. If I'm not mistaken, our exam is on a Monday. Our final exam, not exam 3. So there will be something, I just don't know what it is, but there won't be a specific study guide, kind of like anything else. That's not a good answer. Let me take that back. I will not create a study guide explicitly, but I will create some version of review questions, kind of like we do for most exams. Does that answer your question, or are you looking for a different type of study guide? In which case, let me know. Any other questions today that you guys have on this almost fall-like Wednesday? Does anyone have, I don't want to call it mediocre Halloween plans. I'm going to make my dog wear a costume. She is a bumblebee. She's a bumblebee every year. We should have one costume. Avery asks, it might be a silly question. It's definitely not. But the final is comprehensive. Yes, it is. Usually, it is something like 15 to 20% new material, and then 15 to 20% new, and then a review over everything else with some weights relatively even between exams 1, 2, and 3. Mariah asks, the next open pie period. So the next open pie opens, let's see if I can get this right. I think November 16th. It opens the week of exam 3, like it always has, but it will go all the way through Thanksgiving week. And so it'll be a 2-week open pie period from, I think, November 16th through November 29th. Then we'll have chapter 10 the next week. And then there's another open pie period right at the end that last weekend. Ooh, Miss J says she's going to a haunted house. I hate scary movies. Definitely hate them. So I might watch a lightly spooky movie. I know it's very embarrassing, but it is what it is. Other questions, thoughts, ideas? A haunted car wash. I saw that on Twitter. You'll have to report back if that's super cool or spooky or not spooky. We'd like all the details. Any other questions? Oh, I know what I was going to tell y'all. So I realized this morning, actually I don't know when it came to my life, I updated, so on Canvas, if you look on the grades page, it gives you a letter grade. That corresponds to the letter grade scale in my course. So an A is an 85 to 100. There's that. But I realized I forgot to incorporate the fact that for the weekly assignments, it drops 2 of those scores. When you go into Canvas, you should see that has been adjusted. It'll basically gray them out. So if you have any low scores, you should see that occur. If you have any questions, send me an email or pop into my office hours. Kajal says, ooh, the haunted car wash we think is on University Boulevard. And Jordan says he has to work all day. Womp womp. Wow, that stinks. But hopefully you'll have a good night before that. So any other questions, any other thoughts? Otherwise, we will talk about periodic trends for just a few minutes and then start chapter 8. Oh, wait. I might have missed some other things. Ooh, Catherine asks, in Alex, there is a section called, okay, so Catherine's question is, I think I can actually, there's a section called Deducing Valence Electron Configuration from Trends in Successive Ionization Energies. She doesn't understand how to go about solving those problems. I think we have an example that will be somewhat similar to that on the board. If it's not, I will try to pull one up during this process and solve one of those. So Mariah asks, what is a B in your class, the percentages? So a B and B plus encompass everything from a 70.0 to an 84.9. And off the top of my head, I am uncertain as to where the B plus line is between those two. I hate to give you a false number, but that is also encompassed in there, or you could calculate it off of the grade scale provided in the syllabus. Or Mariah, if you send me an email, I will look it up and get back to you. And if I remember, I'll send you an email either way. Okay, so you guys can keep asking questions. I'll keep taking them today. Today we have 8 questions. 6 out of chapter 7 and 2 out of chapter 8. So, well, that's mostly my head. So our first question, which is not the best work, is to determine I know how to fix this. Determine the length of the bismuth-iodine bond in bismuth triiodide. If the iodine-iodine bond is 2.78 angstroms and a bismuth-bismuth bond is 2.84 angstroms. 2 things to note. 1, at this point in the semester, like today, we don't know how to draw bismuth triiodide. In approximately 2 weeks, we will know how to draw that. So keep in mind, chapters 7, 8, and 9 really are going to kind of all come together. So keep track of that. So hang on to that info. The other thing is I will always provide this information where it tells you what the single bond is. There are some questions where it'll ask you to calculate that. Also totally doable, but you're not required to memorize any of this information. I will give it to you. So when we think about a bismuth-iodine bond, we're looking at the bismuth-iodine bond. If we know that the bismuth-bismuth bond is equal to 2.84 angstroms and the iodine-iodine bond is equal to 2.78 angstroms. Now, This A with a cute little hat on top is called an angstrom. 1 angstrom is equal to 1 times 10 to the negative 10 meters. It's a pretty standard unit. You probably have seen it on some of your equation sheets. It is basically a way for scientists to convert between angstroms or to think about bond lengths in whole numbers. I can think about the difference between something that is 3 feet long and 5 feet long. If you start to tell me it's 0.2 football fields versus 0.25 football fields, I have a hard time processing how much different that is because it's not really a whole number, and that's a little difficult. So an angstrom is that. I will provide the bond lengths in angstroms, so there's that. But we know that half of the bond comes from bismuth and half of it comes from iodine. So the bismuth-iodine bond is 1/2 of the bismuth-bismuth plus 1/2 of the iodine-iodine bond. So it will be 1/2 of 2.84 angstroms plus 1/2 of 2.78 angstroms. And that should give you, we're still on the board, 2.81 angstroms as the length of this bond. So what do we think? Do we have questions about this? Seems kind of simple. It'd be easier if I was not standing in front of it. What do we think? Also, if you have no questions, feel free to drop that in the comment box, which I think is not in that direction. The struggle is real today. So far, I'm not seeing a lot of questions. These are relatively easy. Now, some of you may wonder, well, how could I back calculate that? You can just set up a different set of equations where you can solve for any of these as x if you have this in one of the others. So, nice. So let's make that go right there. I will go ahead and erase this. So our next question is also a periodic trend, and so it asks, which element of sodium, magnesium, aluminum, silicon, phosphorus, or argon has the largest I2? So we're asking about I2, which is the equation of element goes to element 2 plus 1 E minus. So it's the equation of removing the second electron. So with ionization energies, it's super important to remember that you're only ever removing 1 electron at a time. Even if we're thinking about I50, you're still only just removing that 50th electron. So when we think about which of these has the greatest, we are thinking only about I2, but we need to think about which of these elements is going to go from the plus to the 2 plus, destroying the noble gas configuration. So, noble gas configuration is the ability to have achieved octet, which we talk about in chapter 8, but we're going to mix it all together, right? So when they have octet, they're super stable. If you removed an outer electron to achieve octet, taking away 1 more electron is energetically expensive. If you have a set of dishes and someone takes like one that matches, it's kind of annoying and aggressive. If you have 8 matching dishes and 1 other dish, I don't really care if you take my non-matching dish, okay? But we want to make sure that we keep it together. So which of these elements to go from element plus to element 2 plus is going to destroy the noble gas configuration. So it turns out that it's sodium. So sodium plus going to sodium 2 plus 1 E minus is going to destroy the noble gas configuration. Now, if you're like, how did you know that? Well, here's what we got. I need a periodic table. So when we think about the periodic table for sodium, it's 1s2, 2s2, 2p6, 3s1. When we go and remove a single electron for sodium plus, the electron configuration is 1s2, 2s2, 2p6. Because we removed that one extra electron out of the 3s. So it's not favorable, but it's not energetically expensive. When we try to create the sodium 2 plus to go into the 1s2, 2s2, 2p5, by trying to break into that noble gas core, it is very energetically expensive. So we can determine that the largest I2 is this one. Now, we're going to do an example problem in a minute where we can say, like, based on this trend, here's what we see. So what questions do you guys have about question 2, about calculating or identifying an element from a series? Ionization energies. What questions do we have? As always, if you don't have any questions, you can go ahead and drop that in the box, and we will work on question number 3 next. So far, I'm not seeing any questions. I'm not seeing any no questions either. But in light of that, we will go ahead and look at, oh, wait a minute. So David asks, before we move along, what happens to argon? Isn't it breaking the noble gas configuration also? And Ms. J says, can we review why it's sodium? Yes, and I will answer that as well. So David's question, what happens to argon? So if we were comparing the first ionization energy, so I1, then argon would have had the highest I1. But we're comparing the ionization energy to remove the second electron. So for argon, it's already broken into its noble gas core. Once you break into the core, it is still energetically expensive, but it will be more expensive when you remove the second one from sodium, because for argon, we've already created this break, so we're just taking another one out of an already broken core. It's a really good question. So make sure that you're thinking about whether it's I1, I2, I5. I like it. So Ms. J asks, why is it sodium? I like that you're asking questions. So the second ionization is the ability to remove the second electron from our element. So to go from the element in a +1 charge to a +2 charge, when we go from sodium plus to sodium 2 plus, we're destroying the noble gas core. But let's think about, let's look at aluminum. So for aluminum, aluminum plus is 1s2, 2s2, oops, 3p1. So aluminum plus is going to remove this outer electron, 1s2, 2s2, 2p6, 3s2. So we removed a singular electron out of a 1 orbital. So what we know is when we think about ionization energy, when we think about trends, the biggest trend is the break that occurs between the one N equals shell and the next. So for aluminum 2+, we know that it's going to be 1s2, 2s2, 2p6, 3s1. So there's not a big difference here, and we're definitely not breaking into that N equals 2 shell. When you break into the next shell, it is much more energetically expensive. So Peach asks, if it were I3, you would look at the third electron removed. Correct. So if we asked for which of these had the highest I3, the answer would not be sodium. So it matters which of these it is. So for I1, it would be argon. For I2, it's sodium. For I3, it would be magnesium. So Camilo asks, are you going to be asked to rank them based on their I2 or just I1? Just I1. So it's easiest to rank them based on the first ionization energy because they follow the trend. You can look at a significant section of them and ask which one will have the largest, in this case like we did here. But for a ranking question, it has to be the first ionization energy because once we get past about I3, some of them have broken into the core, some of them have not, and so it gets harder to determine whether or not that's an equivalent playing field. These are great questions. Does anyone else have any questions, or what questions do you have about ionization energy? In general, in specifics? And I think in this case, we're going to reorder these questions. We are going to move to question 4 instead of question 3. So Ms. J asks, how do we know we have to cut into their next shell? It's a good question. We can use the electron configuration. So the electron configuration of these is going to tell us when we're moving into these. And so as we think about the electron configurations that we learned last chapter, we're going to use that to guide our thoughts about ionization energy. Ooh, Kajal, I like that it's starting to make sense. So let's look at number 4, because I think this will help. So which of the following elements, neon, sodium, magnesium, aluminum, or silicon, has the following ionization series? And please justify your selection. So please note that you cannot see my pointing because this is the way the picture is. It goes I1, I2, I4, I4, I5. The first I4, the one that corresponds to 7,733, should be I3. It just happened. So let's think about this and use this to kind of guide our thoughts. So when we look at these trends, so the trends tell us how much energy, and in this it's in kilojoules per mole, which is great. Sometimes you'll see it in kilocalories per mole. You can just think about it as energy is energy. But I1, I2, I3, I4, and I5 is removing a successive electron every time. So we can start to think about, okay, well, if we have to remove an electron, what do we do with this information? So this pattern of values here, we can see that it goes 700, and then it doubles approximately, and goes to 1,400, and then it goes to 7,000, so it goes up by 5,000, then up by 3,000, then up by another 3,000. So we can see that the biggest gap is between I2 and the I4 mislabeled as I3. The I3 mislabeled as I4, right here. So in order to identify our element, we need to figure out whose noble gas core is being destroyed right here. So my suggestion, the way I solve these, is to write down the start with this. So I1 is your element goes to E plus 1 E minus. Oops, I2 E plus. So every time we remove a single electron, and in this case, E is just for any element, not the element E. So when we think about this, we can see that the largest gap goes from 2 plus to 3 plus. So when this equation happens, so that tells us that this destroys the core. So now we can go back and start to look at the electron configurations of any of these ions. We know that electrons are last in, first out. So not necessarily how we think about a lot of other things where it's in, first out. So it's last in, first out. Yes. So now we can start to think about, so what are some of our options? Silicon, aluminum, magnesium, neon, and sodium. I'm missing one of those. Aluminum. So one of these 5 elements, when we look at this, is going to be breaking the noble gas core. There's 2 ways that you can think about that. You could write out the electron configuration of all 5 elements and remove 2 electrons and then figure out what you got. The other thing to think about is which of these elements preferentially prefers to be a dication. What do I mean? Which of these wants to be 2 plus? So we know that going from 2 plus to 3 plus breaks the noble gas. So which of these preferentially wants to be a 2 plus ion? So if we think about achieving octet, or when we talked about the periodic table, right? So sodium wants to be +1, so it can achieve octet. Well, magnesium prefers to be 2 plus, aluminum prefers to be 3 plus, sodium plus, neon never wants to lose an electron, so that doesn't make sense in this case, and silicon would prefer to be a 4 plus to have achieved noble gas configuration, or to having octet. You can think about it either way. So based on this information, we can think about the electron configuration of magnesium, which is 1s2, 2s2, 2p6, 3s2. So when we lose 2 electrons, if we've lost these 2, we just have left the noble gas core. So once we remove that 3rd electron, we're going to destroy the noble gas configuration. So as we think about this, what questions do we have? Oh, so the right answer is magnesium, and your justification could have included any number of, sorry, trying to be in the frame. You could have talked about the destruction of the core in this case, how magnesium prefers to be a dication, any number of those things. So with this question, tied with the one from before, how do we feel about ionization energies now? What do we think? Was this, not what do we think? What questions do we have about ionization energies? And what questions do we have about this problem as well? So far, I'm not seeing many questions. Ooh, thanks, Angela. It's always nice to know that this was clear. Nice, Avery. While a few more of you maybe chime in, I'm going to go ahead and erase the board so that we can look we're going to go back to question 3 next. Nice. Miss J, that is totally correct. It is magnesium because of the 2+, because once you create the 2+ ion, it's going to destroy the noble gas when you go to 3+. Peach, that is totally correct. I would accept that and give full credit. So our next question is, which element of sulfur, chlorine, arsenic, selenium, bromine, argon, or krypton has the strongest electron affinity? So when we think about this, electron affinity is the ability of an element, E, so Ea is our element plus an electron to create E-. And so in this case, which of these is going to have the highest electron affinity? We know that electron affinity increases as you go across a row and up. So in this case, of the elements that we have, chlorine has the highest. Electron affinity. Keep in mind that there are a couple of exceptions to the rule. Elements such as nitrogen. Nitrogen does not want an extra electron because it now violates Hund's rule. So nitrogen would prefer several electrons versus just one. So questions about, or what questions do we have about question 3? So which of these has the strongest electron affinity? And if you don't have any, let me just go ahead and write that and we'll keep on trucking on down. Thanks, Angela. I'm glad you don't have any questions. So Mariah asks, how do we explain our answer since all we do is look at the periodic table? So you can talk about how or why any element has a strong electron affinity. So chlorine has the highest electron affinity as it is most likely. So the orbitals are closest to the nucleus, as well as the fact that it prefers to accept a single electron to achieve octet. Mariah, that's a good, I like your answer there. Okay. So Catherine asks, can you explain how I know it was chlorine? Yes. David asks, what does electron affinity mean? Good question. And Miss J asks, is Ea always going to be -1? Miss J, are you asking, is it one electron added at a time? Or is it always going to create a negative element? So follow up with that. David, I'm coming back to you, Catherine. Hang tight. So electron affinity is the ability of an element to accept an electron. So I like to think about it. Now, imagine pre-COVID land. You're on UNF's campus. You walk by the student union. Somebody's out there with flyers. Now, they're handing them to you, right? Just handing out papers left and right. Your options are to put your hands in your pocket, and they will still try to hand it to you, right? Or you can take it, and then you can throw it away or something else. Electron affinity is the ability of an element to accept the electron. Some elements, those on the right side of the periodic table, have a higher electron affinity. Some elements have an electron affinity that is positive, which basically means that they will not accept it. These elements are elements such as noble gases or elements in the S block. So sodium, magnesium, elements over there. If you give sodium an electron, it basically gives it back. It's like, no thanks, I don't want that. So electron affinity is how much, not how much, but what is the energetic cost-benefit analysis of accepting an electron. So the equation is the element plus 1 electron gives us E minus. So now we're back to you, Catherine. Catherine, the reason chlorine has the highest is because it is furthest to the right on the periodic table. So it's all the way on the right side. And the higher up you go in the table, the stronger the electron affinity is. So the reason the electron affinity is higher, perhaps with fluorine and chlorine than anything else, has to do with the proximity both to the nucleus and how much stable something is when it achieves octet. So, right. So it's not argon because that's a noble gas. So a noble gas will not accept an electron because they already have octet. And it's kind of like when you add something else and then you have to like start a new table. Nobody wants to start a new table. We want to add seats at the table we have without reaching into the next table. Good questions. All right, so Ms. J asks, is it going to be like adding an electron at a time? So Ms. J, it's always one electron at a time. Both electron affinity and ionization energy are just either adding or removing one electron at a time. Okay. So Jordan asks, wait, Camilla, we're going to you first. Jordan, I'm coming back. The trend is increasing left to right and bottom to top. Yes, but there are some negatives in there, such as nitrogen. Anything with a half-filled shell will not accept an electron. But the further you get from the nucleus, the less strong electron affinity is across the board. So Jordan asks, I'm going to read all of yours, but y'all can see the comments. Hold on. Just like that. A few questions. Jordan, I'll take a look. So Jordan's asking, do you have to master all of your topics or just learn them? You need the entirety of your strip across the top. So you need to have 100% pi in order for that to be finished. So if you've mastered or learned, and there is a difference, and I'm going to have to look into that, but when you sign in, if it says 100% pi, you get all 100 points. For the on time is totally different, but the knowledge checks will remove any objectives that you did not master, you just learned. So, master your final topic. Jordan, I'm going to have to look into yours. Feel free to send me an email to remind me, but I will do that after my other class, since I have class at 4:30. But it should let you do that. It may require you to do that. I cannot control Alex. I can try to manage it, but I'll take a look. You should just have to complete your pi. I think that's right. But if it's asking you to do a review, you may have to do that as well. I will look into that. Okay, well, let's take a sidestep out of periodic trends and talk about Alex. So right now, there is a set of objectives about Chapter 7 and part of Chapter 8, right? So this week, you need to learn all of those objectives. In 2 weeks, I think, you will have a knowledge check. That knowledge check basically asks, did you actually learn this? The idea being that sometimes, and for some of you, what you've noticed is Alex really only has 10 to 12 questions. You can write down or take screenshots of all of them. And then basically cycle through it long enough and you'll eventually get 5 right in a row, or 3 right. However, when you go back, it will take those away from you. If you turn them all in, if it tells you, like tonight, you finished your objectives, that's 100% on time. The ones, if it takes it away from you after you've turned it in the first time, that only affects your pi score. So those 2 scores are different. And if you have questions, feel free to pop in my office hours. It's really easy for me to look in there and see if you've missed a bunch. If you're missing 1 objective a week, occasionally, not every week, but some weeks, then likely that means that you will still get either all or most of your on-time points. So it is per objective, not per week. So if you turned in 9 out of 10, you got 90% of them turned in on time, which is above the 85%. The pi, by the end of the semester, so that next open pi time, you want to make sure that you've caught up on anything the knowledge check has taken. It should, if you've already finished most of it, eventually convert to mastered. It may be telling you that there are things it doesn't think you know all the way yet. I will go in and look, but that's what that looks like. So Mariah asked, does the mastered learned affect the time in which they're submitted? No. Does that affect your grade? Jordan, it should give you one. We'll talk about it via email because I think something weird might be happening with yours if you've already finished all those. So Mariah's on board. Jordan, I think you may have to wait till the next knowledge check. I'm not entirely certain. But Mariah, I do want to go back to your periodic trends question, which said fluorine has the highest affinity of all the elements. That is correct. Okay. So if we have more Alex questions, let me know. I feel like we're at the point in the semester where we all have a few like, how's this going to work questions. I'm happy to answer this. So the next 2 questions are kind of coupled together. So we want to write the equation for the 4th ionization of lead and the 3rd electron affinity of carbon. This, I think, helps with the questions that a couple of you have had about what does it mean. So in this case, when we think about the 4th ionization of lead, we know that that's talking about I4. Whatever this little number is the charge that we can expect on our element after the arrow. So in this case, we're looking at lead, which is Pb. So we're going to go from Pb 3 plus to Pb 4 plus. So all it's asking for is the ionization energy, right? So when we think about the electron affinity, the 3rd, we know that we're going to be adding the, where are my notes? Sorry. Adding the 3rd electron, so we know that the charge here is going to be 3 minus. Oh, we got to move that over a little bit. So we're going to take our carbon 2 minus plus 1 E minus gives us carbon 3 minus. Now in the book, if you're reading along, it uses the gas state and all of these. They're all gaseous. I don't feel the need to write that. As long as you don't put that it's something else, I don't care. You can either add gas to all of these elements or leave all of them off. They're equally correct. But I will be asking about these on the exam because I think it's an important aspect to really think about what this is. So Alex will sometimes ask you questions about how these interact with one another. I think it does. I'll have to look. But think about this as ionization energy is removing an electron. Electron affinity is adding it back. So they are related to one another. So the ionization energy is equal to the negative electron affinity. Usually, it's not always true. It can be significantly different. But to remove an electron is equivalent in energy of adding that electron back, just with the inverse sign. Think about delta H. So what questions do we have about writing the equations for either of these, either electron affinity or ionization energy? So far, I'm not seeing any, which is a good and exciting statement. So Ms. J asks, is there a difference between 1 E minus and E minus? No. That's just a number 1 in front of the E minus, so you can have it with or without, as long as you're just removing 1 at a time. Nice to know that it's pretty clear, Kajal. Anybody else? Any other questions about these two? What would be the electron configuration for lead? Sure. So the electron configuration for lead 4+ would be the xenon core 6s2 4f14 3 4 5 5d. Hold on, we'll just do lead first. 5d10 6p2. So when you remove electrons, they leave from the highest n orbitals first. So the Pb4+ would be the xenon core 4f14 5d10. Because you lost both the p and the s electrons, even though they were in opposite orders. So because they're both in the n equals 6 shell, those come out first, then the 5d orbital, then if you were to have removed 14, if you removed more than 14 electrons, then you would remove out of the 4s. Good question. Any other questions? Happy to help. So next, we're going to start drawing the Lewis dot structures. So as you might have noticed in the video, for Lewis dot structure developments, there are only 8 options. You can have 1 through 8 valence electrons. We don't draw Lewis dot structures of transition elements or anything in the F block. Those do not have the same type of valence electrons that we tend to think about. Element has the largest ionization. Ms. J, I think that's correct if I'm interpreting your question correctly. So in this case, we want to draw the Lewis dot structures for these 4 elements. Tin, bromine, aluminum, and sulfur. So the first thing we're going to do is write down the number of valence electrons for all of these. Valence electrons only come from the s and p block elements. So you can basically, on your periodic table, count across how many seats it is to get to any element. Or you can write out the electron configuration and only total the s and the p elements. So in this case, for 10, there are 4 valence electrons. Bromine has 7 valence electrons. Aluminum has 3 valence electrons, and sulfur has 6 valence electrons. So VE, you're going to see that like a billion gajillion times, stands for valence electrons. So now we can start drawing our Lewis dot structures. So 10, and I'm going to try to draw these big enough for you to see them, because like it's kind of hard, but I'm not asking you to draw mountains on the side of your page. So there are 4 valence electrons, 1 on either side until you've used up all of your valence electrons. So that's 10. So for bromine, same difference. 1, 2, 3, 4, 5, 6, 7. Now, you could have easily rotated the single electron around on any given side in order to make that be the singular lone electron. It doesn't really matter where it is as long as your elements are set up in this way. So Lewis dot structures have some rotatability to them where the lone pair or an empty side might be. As long as you follow the rules, there is nothing that says that you couldn't have had 2 on this side and 1 on the bottom, if that makes sense. So for aluminum, we have 3. Whoops. And it looks like this. So again, the empty seat could have been on any of the 4 sides. It doesn't have to just be the bottom, the side, any of them. It's rotatable. So for sulfur, we have 6, 1, 2, 3, 4, 5, 6. Now sulfur, it does need to follow some rules. So valence electrons in my course, I teach it, that they sit across from one another on all 4 sides and then the same. So in this case, your 2 lone electrons need to be on opposite sides and they cannot be a pair. So Ms. J asks, do we get the number of valence electrons from the electron configuration? You can get it from the electron configuration or from the periodic table. So I really wish I had the ability to like plop one in here, but this is what we got. So in this case, we know that everything in this column has 1 valence electron because there's only something there's a single electron in the s orbital. If you were to come over to the noble gases, we know that they have 8 valence electrons because they have a full octet. So it is just the s and the p block elements that total up to make the valence electrons. So you can annotate your periodic table across the top if that so speaks to you. Everything down here in the transition metals, it's really, really hard to draw the valence electrons because they don't follow the rules. So like, you know how I've called these the no rules kids all semester? Still true. It will be true until the end of time. But they do not have valence electrons the same way that we think about it. So valence electrons are just S and P. Good question. Other questions about Lewis dot structures for single elements? Or what other questions do you guys have about it? Not seeing any, but if you have some, I'll answer them. So the last thing we're going to do today is to briefly, we have 3 of these, and I think after we finish the videos that will come out this week, the way I'm going to teach you today doesn't make a lot of sense. So we're just going to think about the idea that now elements can stick together. and make molecules. Could y'all? Sames. Every semester, I live for chapters 8 and 9. They are my favorite. I have these huge models. Maybe I'll bring them in 2 weeks or next. We'll see. I'll have these models. They're like yay big. They're amazing. Now, totally off topic. But today, we're going to start to think about how any of these elements can fit together, like Legos. Legos, if you buy like Lego brand Legos and any other brand of Legos, they sometimes don't quite fit together right. So they have to have some compatibility. 2 electrons makes a bond. We're also going to learn that sometimes 4 electrons makes a double bond and 6 electrons makes a triple bond. Today, single bonds are our only option. But we're going to think about these 3 elements, and we're going to fit them together to create a molecule. But before we do that, David asks, what do I think is the hardest topic in Gen Chem 1? I think a lot of students have issues with titrations and molarity. So I think that's hard, and limiting reactants are probably the hardest 2 topics that students see in Gen Chem 1. I think this one, if you are not a mathematician, if math is like just something you have to do, I think this starts to bring our chemistry into 3D space, and most of us like to be able to think about stuff that we can picture. Good question. So for the next couple of seconds, we are going to draw these molecules. If you've looked ahead in the chapter 8 slides, and as I've been working on the chapter 9 material, so it is not true in these cases or on that handout, but most of the time I will tell you what is the central atom. Most of the time, it's the first thing that you see. It's kind of like, so although in the first element it's not, so that's totally a lie, but for PCl3 and CH2Br2, those are the central atom. I will tell you what the central atom is by underlining it, because I think that's helpful. So the underline means that that is the central atom, or I will try to use words to tell you how they connect. But that only kind of works. So let's look at H2S. So when we think about this, we can think about the Lewis dot structures of hydrogen and sulfur. So one thing we can note is that we have 2 hydrogens with a single electron and sulfur with 6, where you could kind of imagine that this could create a bond and this could create a bond. So what I'm saying is, if a bond requires 2 electrons, and you could see where the hydrogen and the sulfur can both combine to create a pair of electrons, we could end up with this structure. Where there are 2 electrons in this bond. Now, what we'll come to see and start to do more naturally is to check for octet. Today, we're not going to do that as much. Next week, when we draw like more compounds, and the following week when we draw even more compounds, that will become much more ingrained. Today, we're just going to kind of assume that they will get octet if we draw them in the right way. So that's our first molecule. Our second molecule is PCl3, with phosphorus being the central atom. So phosphorus has 5 valence electrons, and chlorine has 7. So when we stick these together, because it's just puzzle land. It's like a Sudoku, or if you are good at those Rubik's Cubes things, it's kind of like that. So we just can see that we could imagine that these chlorines could interact one on either side to where you would get a molecule that looks like this. are the 3 chlorines? Let me. All right, hopefully this won't make you too nauseous. Sorry. Good enough. So as we can see, we have a phosphorus in the center with a single lone pair of electrons, a bond at 90 degrees, so 3 bonds, 2 chlorines that all have 3 pairs of lone pairs. So around each of these elements, they have 8 electrons. Now, no one's asked, hey, Dr. Malcolm, can we just get rid of the 2 dots and use a line? No, because it turns out that when you do that, it means something different to chemists the further along you get in your chemical career. So we want to draw lone pairs of electrons, i.e., I will expect you to draw lone pairs of electrons on your exams. So you can imagine that our next exam is going to have a lot more things where you just write your initials in the blank and I grade your short answer work, right? Because I think there's no way for you to draw this. Like, how would you draw that on Canvas? Like, that's never going to work. But you can draw it on your paper and I can grade it. So that's what PCl3 looks like. So when we think about the last one, we're going to take our carbon central atom, which has 4 valence electrons. We have 2 hydrogens, which have a single electron, and 2 bromines, which have a single lone electron. So we could start to put this central atom carbon in the middle, and we're going to connect 4 things to it. And those 4 things are 2 hydrogens and 2 bromines, both of which have a single electron. So we can just stick them onto the edge of these. So now that's the structure of CH2Br2. Now, it's possible in high school chemistry or in a different chemistry class, or if you just love chemistry and have been like reading the book, you're like, there are not 90-degree bond angles. That is true. 90-degree bond angles are in fact only found in Lewis dot structures. So the difference between Lewis dot and VSEPR, which we will learn in chapter 9, so hang tight, the difference between those is the ability to go from 2D space to 3D space. In order to get to 3D space, we've got to pass through the 2-dimensional space. So this is our first foray into how to draw a Lewis dot structure. In the next batch of videos, I don't remember what number it is, but one of those videos is going to be on drawing Lewis dot structures more complexly, thinking about the guidelines for how to do that. This is more puzzly, so if you don't like this method, you may like the next method and it will make much more sense. So what questions do we have about basic Lewis dot structures or periodic trends before I attempt to access my ALEX in order to look for the topic that someone asked about at the beginning of class, which I will actually try to do while you guys, if you have any questions. If you don't have any questions, there are no other topics that I have prepared for you today. So now we can all watch me go to the internet and try to get to Alex. All right, let's go back to the topic. Deducing valence electrons configuration. I should stop doing that. I think if Catherine is still around, I'm going to try to answer your question. I'm not going to try. I am going to answer your question. So you earlier asked about the deducing valence electron configuration from trends in ionization energies. So we did a question somewhat similar to this in, I think it was number 4. So instead of giving you a table, it gave you a bar graph. So the bar graph in this case would basically look like this, or some of them. And then it says like I1, I2, I3, I4, and I5. And so in this case, what we see is it tells you, hold. So once it gives you this, it tells you which period it is, which is basically code for which row in the periodic table. So we know that because this shows our largest gap, this movement here breaks the Ng core. So we know that the I3 element, so in that case, it would likely be aluminum if it was out of the, that's not right. It would be boron. So in that case, it would likely be, if it was out of the period 2, boron, because B3+ is the preferred state. So once you do this, this is your big gap. So hopefully that helped out. Anybody else have any other questions? Otherwise, I will see you guys all right here, not at this right now, but I will see you guys next week on Wednesday where we will talk about the end of Chapter 8. I hope you guys have a great rest of your week. Don't forget I have office hours on Friday if you need help or want help. Y'all have a great day.